Okay, thank you very much, and thank you to the organizers for the invitation and also for organizing this very wonderful meeting. So this is sort of like a survey talk, but not really, because I will actually not state very many theorems. So it's rather a perspective on the Fibonacci trace map, and so maybe the other part here is developed with Anton Gorodetsky. So we started to work on these things pretty much exactly 10 years ago, so in 2007. And so we have proved a number of results, and some of them will be mentioned. But that's, again, not really the point of the talk. The point of the talk is how we view the work and the results and how everything actually works. And so that's what I want to explain today. And so specifically, I want to present a number of models and then explain how you can treat them simultaneously, basically within the same framework. And I want to make very explicit what the model-dependent input is. Okay, so the first part will just recall the Fibonacci substitution that we have seen many times. And then introduce these operators. Okay, so the substitution is the following, as we all know. So it maps A to AB and B to A. And then you generate the substitution sequence and the associated subshift. So you define the words SK, which are the substitution K times applied to the letter A. Then, of course, because of the substitution rule, they obey the following recursion. And so from that recursion, you see that as you write down these words, all you do is add on top of what you already have, and therefore there is a natural limit. Okay, so, and of course it looks like this. So this is an A, B to the Z plus. It's a one-sided infinite sequence of A's and B's. And then the subshift, actually I want to consider the two-sided subshift. So I look at the two-sided sequences so that each factor or subword of omega is a factor of U. And in fact, by uniform recurrence, the set of factors of omega is equal to the set of factors, not only contained. Okay, so that's the Fibonacci substitution, the Fibonacci substitution sequence, and the Fibonacci subshift. So all these things we've seen many times during this conference. And so the associated operators are the following. So the first ones are discrete Schrödinger operators. And this is in some sense the default class. So this is the first class of operators that was studied intensively starting in the 80s. In fact, the paper introducing them, or the papers, appeared even before the discovery of quasicrystals was officially published. But the progress that I want to describe today really is more of a development of the past 10 years. But still, so the operators are the following. So you take an omega in your subshift, and then it's a two-sided sequence. And so for each n in Z, omega n will either be A or B. And so you map that to real numbers. And in fact, I just want to normalize things. so that the two values I take are lambda and 0. Okay? So you can take any two real numbers, but then you just translate things so that one of them is 0. And so this is now a real valued sequence, v omega, that you have for each little omega. And with this sequence, you write down an operator that acts in L2 of z. Okay, so the psi is an L2 vector, and h omega of psi is exactly that. And so these are the discrete Schrödinger operators that have been studied since the 80s. All right, so I want to introduce 4 classes of operators because these are the ones that are of separate interest. And so the point is, whenever you work out what the Fibonacci case gives you, the results should be judged from the perspective of the field in which the operators arise. Okay, so my second class is Jacobi Matrices, which is actually a generalization of this class of operators. But the motivation for studying that is twofold. One is they arise in the study of orthogonal polynomials on the real line. And the other one is they arise in inverse spectral theory. So if you start with operators of this form and study their spectral properties, and at some point decide to invert the whole thing, start with spectral information and ask which operators they come from, you're naturally led to this generalization. It's actually not well understood which spectral information leads you back to discrete Schrödinger operators. You will always go back to Jacobi matrices, which are a bigger class. Okay, so it's basically the same thing. So here we have 2 sequences. AN and BN. And each one can again be defined for each omega in your subshift in the same way. So the idea is that the A's are positive real numbers, and they arise from the A's and B's in your omega by local substitutions. And again, the easiest case is like in my first example, where you have letter-to-letter substitutions. You can look at sort of more general cases that makes the analysis much more complicated. So yeah, just for simplicity, if you see an A, you write down a positive number. If you see a B, you write down a different positive number that gives you your sequence A. And here you do it in the same way, but the restriction is just that they are real. And so then the operators look exactly the same. It's just that the A's give you the off-diagonal elements. So A omega n, C n plus 1, plus B omega n, and A omega n minus 1. Okay, so if the A's are 1, you get discrete Schrödinger operators. In that sense, it's a generalization. Discrete Schrödinger operators are studied as a class because they arise in quantum mechanics in very simplified situations. You have to be in one dimension, and you discretize space, and you arrive at these operators. So it's well motivated to study them. But as I said, if you start to study inverse spectral theory, you really should work in this class.
So okay. Are the A's and B's functions only of the letters?
Exactly.
So they take in most 2 values each?
Exactly. Okay. And as I said, you can generalize your setting where but then the analysis is actually much more difficult. Yep. Okay, so then the third class is continuum Schrödinger operators. So here the motivation is similar to the first class. If you are interested in quantum mechanics, then you study Schrödinger operators. And as I said, if you would like to simplify your situation, you look at one-dimensional examples. And so both 1 and 3 are one-dimensional Schrödinger operators. But then the last decision you have to make, discrete or continuum. And so generally the theories are very much in parallel. The results are very similar. However, proving things in the continuum case is just technically more demanding. And so here in this particular setting, it will turn out, or it has turned out, that the continuum case is just much richer. And we will see that explicitly in the explicit quantities that we'll discuss. Anyway, the idea is similar. So you have operators. Now this will be in L2 of R. Okay? And so if you look at this operator there, it really has a structure of discrete Laplacian plus multiplication operators. So you do exactly the same thing here. So you take the continuum Laplacian in one dimension, and then you have an omega-dependent multiplication operator. And now how does the Fibonacci sequence enter? So here we just took this AB sequence and replaced them locally by real numbers. But here, of course, you have a function on R. And so what we will do is replace each A by some local potential and each B by some local potential. So where V omega arises from omega by replacing the A's and B's by two types of local potentials. Okay, so the easiest case, of course, is if you just take constant potentials. So if you see A, B, A, B, and you place an obstacle for each A, and you place no obstacle for each B, then this is how your potential would look like, okay? So you take two local pieces and concatenate them according to your sequence omega. That sort of defines a function on the real line that you use as a multiplication operator here. Okay, so that's the third class. And the fourth class is CMV matrices. Yes, because, sure, I mean, no, well, yes and no. So you could, in principle, take an unbounded local potential here. That's, again, not the point.
Number 2, you don't say they're bounded there.
Yes, but they are, because you only have A and B, and you do letter by letter replacements, and so your sequences take two values. Okay, so. All right. So CMV matrices. So here, so really the main thing I have to tell you is how to go from omega to the parameters of your operator, then how the operator looks, and then why people care. Okay, so here it's very much the same thing. So here you have alpha, omega, a sequence in the unit disk, in the open unit disk. So those are the W's and C of norm less than 1. And again, I will do letter by letter. So I have two values that I pick in the unit disk that I just list according to my sequence of omegas. Okay, so that's the simple case. And then, well, maybe I don't want to. So I will not give you the matrix. So if you are really interested, just Google CMV matrices. But that's not really the point of the talk here. It's a little difficult to write them down, but they are 5 diagonal, and the entries are functions of the alphas. Okay, so there's really no point in writing down the full expressions. But yeah, so here, these are tridiagonal matrices. These are 5 diagonal matrices, and all of them act in L2 of Z. Okay, but the difference is that this is a unitary operator, and all these operators are self-adjoint. Okay? And so while the Jacobi matrices arise in the study of orthogonal polynomials on the real line, well, because measures of self-adjoint operators happen to live on the real line, CMV matrices are the canonical matrix model for orthogonal polynomials on the unit circle. Okay, so therefore they have to be unitary because their spectral measures are the measures with respect to which you consider the orthogonal polynomials. Okay, so this is really a unitary analog of number 2. Jacobi matrices are the canonical matrix models for measures on the real line, and CMV matrices are the canonical matrix model for measures on the unit circle. Okay, and so really, from the perspective of this talk, you ask what you get if you take your coefficients according to an element of the Fibonacci subshift. So that's the point of this example. And number 5 is quantum walks. So here I will even be less explicit than in the previous case. So these are quantum analogs of classical random walks. So in general, but in our setting here on Z. Okay? And so in the classical case, you have a coin, you toss it, that determines if you go left or right, and you do so with probabilities p and 1 minus p. For the quantum analog, you have a spin, and then you have a U2 matrix that you apply to the spin, and that tells you how you move left and right and how you adjust your spin. So that's how it works. And the reason why I don't tell you how they actually look is there is a way, can be transformed, or related to rather, C and B matrices. Okay, so from this perspective, they're really a subcase of the previous case. And however, they are of relevance. So people study them. So for example, quantum walks move faster than random walks. That's why people, that's one reason why people are interested in them. And so from our perspective, the question is, well, what can you say about a quantum walk with coins listed according to a Fibonacci sequence? That's the question that you could ask.
Does that mean it's not associated to a wave operator?
It is, in some sense, yes.
But it travels faster than the speed of light? Is that what it means?
No, it travels ballistically, but a classical random walk travels diffusively, so in that sense it's faster. Yep. Okay, so those are my classes of operators. And so my goal, again, is to look at each of them in the case of the Fibonacci sequence. Okay? And so the common results for all these operators are the spectrum of each of these operators is a Cantor set. And of course, for continuum Schrödinger operators, the spectrum is unbounded. So in that sense, it's a generalized Cantor set. It's an unbounded Cantor set. It's a Cantor set of zero-Lebesgue measure. Okay, so that's one thing you can prove. The second thing you can prove, all these operators are either self-adjoint or unitary, so therefore you have spectral measures. And the spectral measures are purely singular continuous. Okay. And 3, transport is anomalous. Okay, so maybe the first 2 statements are more or less self-explanatory. What does the third one mean? So in the first and third, Schrödinger operators are of interest because they drive the Schrödinger equation, which is sort of the central evolution equation in quantum mechanics. And that's exactly the transport you're interested in. You have a quantum state. It changes over time according to the Schrödinger equation. And how does it change? And so the claim is that the change is anomalous. That's sort of a term that's being used. And that just means that it's different from all the classical ways in which quantum states could move in crystals, in random media, in whatever. Okay, it was a new type of transport phenomenon in the Schrödinger equation. And so for the first example, the discrete Schrödinger case, this was proved in '89. This was proved in '99 for the discrete Schrödinger case. And this was proved in 2007. Okay, so this is only for the first example. And then the same results were then later proved for the other cases, which are more difficult. And hopefully in the talk will become clear why it's more difficult. But still, there is this common approach that you use, and you see exactly where the analysis becomes more difficult. Okay, so this is transport in the Schrödinger equation, but you can also use a Jacobi matrix to look at the time evolution given by the unitary group. For CMB matrices, the time evolution is just given by taking powers. And same thing here, the quantum walk operator is a unitary operator, you take powers, but that's exactly the time evolution that you're interested in when you're looking at these walks. Okay, so you have some initial distribution, and then you quantum walk, and then you ask how fast you're spreading, and the spreading is anomalous. And so the thing is that if you work in any of these areas, you may not know or even care about the Fibonacci case. Okay, so if I work on quantum walks, I may not have heard of the 2007 transport as anomalous result for discrete Schrödinger operators. Okay, but I may care about an example where my spreading is unusual. It's not diffusive, it's not ballistic. And so therefore, for people in quantum walks, it may be of interest to exhibit this example coming from the Fibonacci substitution where you have anomalous transport. That's one of the motivations for working out these analogs for these different models. Similarly here, for CMB matrices, so they received a big boost about 15 years ago when Barry Simon started to work on that. But honestly speaking, proving this result in the CMB context was really a surprising result because people hadn't seen zero measure spectra up to that point. Okay, so even in the Schrödinger case, up to the 80s, people didn't think that you could have zero measure spectrum. Now, people in the Schrödinger community say, sure, it can happen. But people in the orthogonal polynomial on the unit circle community hadn't seen that, and to them it's surprising. So they care less about transport because it's a less natural question, but you can still prove the analogs. Okay, yes?
Is there anything special about the Fibonacci substitution?
Yes?
Okay.
Good question. So I was actually going to preempt that, and I forgot. So when I wrote down the substitution, I actually wanted to say, yes, I know that the question is coming, why Fibonacci, why not other substitutions? And so the next part of the talk will introduce something that you basically have for Fibonacci type substitutions. Okay. So actually the part after the next part. So the second part is just the trace map. So the common thing, so all these operators have generalized eigenvalue equations that lead to 2x2 transfer matrices. So that's the first important realization. So this is, of course, well known in the first two cases. Sorry, also here, it's also well known here. But here it's not obvious at all, but it's true. So you can actually realize them using 2x2 transfer matrices, even though they are 5 diagonal. The 5 diagonal structure initially suggests that you have 4x4 transfer matrices. But there's a way of reducing things to 2x2. And that's really important. Okay, so, oops. Okay, and I will show you that in the case of the first example, and in the interest of time, not explain how to do it in the more difficult cases. So, but the first case, discrete Schrödinger operators, is the classical case, and there, of course, everybody who has ever looked at them knows that you want to look at these transfer matrices. And so here's how they arise. So what is the generalized eigenvalue equation? You're looking basically at solutions of operator applied to function is equal to some eigenvalue times the function. But it's a generalized eigenvalue equation because you do not require U to lie in L2. You look at any solution of this equation. And so once you have that, then you see that anything goes. I mean, you can just prescribe any two values and then use these matrices here to go from one step to the next. Yes, I am. Thank you. Right. Thank you. Okay, so this is just an equivalent formulation of the transfer matrix. And now, so if you have your potential, and of course it's generated by this sequence omega from the Fibonacci subshift. But everything that you get in the Fibonacci subshift is in some say the limit of these SKs, these S to the KA, and so they show up everywhere. So just go to a location where your potential on some interval is determined by one of these words SK. Okay? And then you look at this 2 vector here and map it to that 2 vector by the product of the FK matrices of this form. And what you see here is exactly the image of the A's and B's at the various locations. Okay? So this product of these matrices is called MK, which really depends on E, and sometimes you don't make that explicit. Okay? MK of E is the product of these guys along the letters in SK. Okay? And so because you have SK plus 1 is SK minus 1, and maps are, of course, composed from right to left. As you compose these maps, you keep tacking on things on the left. Things turn around. And so MK plus 1, in fact, is MK minus 1 MK. Okay? So this is the recursion for these matrices across the SKs that comes directly from the substitution. Okay, so, right. So, good. So you see here that the matrices are 2 by 2. As I said, in examples 4 and 5, there's a way of turning things into a 2 by 2 situation. And then another thing, so the MKs are always chosen so that the determinant of MK is 1. Okay? So here you get it for free. This matrix has determinant 1. These products have determinant 1, so there's nothing to do. But if you try the same game for Jacobi matrices, you will see that the determinant is not 1, and you have to do something. And again, in the interest of time, I actually thought I should explain that, but I will skip that. So for Jacobi matrices, there's actually a trick how you associate matrices that are still relevant, but now have determinant 1. And here, these transfer matrices here, while being 2 by 2, still don't have determinant 1, so there is another trick. So that's what I'm saying. So if you sort of go through these progressions of examples, you encounter more and more places where you actually have to do something to recover some key features that you got for free in the first case. Okay, so that's really the main message. But once you have that, so this determinant equal to 1 implies the following. For xk, which for historical reasons is 1/2 the trace and not just the trace, we have xk plus 1 is 2xk, xk minus 1 minus xk minus 2. Okay? So plus Cayley-Hamilton. Okay, so if you use that the determinant is 1, and you use the Cayley-Hamilton theorem, that if you plug the matrix into its characteristic polynomial, you get 0, in 4 lines you can deduce that identity for the half traces. Okay? And that in some sense is the Fibonacci trace map, but that's not how we want to view it. But this is how the Fibonacci trace map was viewed until 2007, when Anton Gorodetsky started to work with me on this. So up to 2007, the trace map was just a recursion for the traces, which is fine. You can get a lot of mileage out of that. And as you see, all these results were proved by 2007. So you can prove all that without actually doing what I'm about to explain. But once you want to go beyond that, then it's very beneficial to do what I'm about to explain. So it's really a shift in perspective, but that gives you something. So, sorry. Okay. In other words, so this is just a very innocuous shift of perspective, but that's the thing that makes things go now. So how do I pass from xk minus 1, xk minus 2 to xk plus 1, xk minus 1? Well, of course, these two you can just read off. Those are the first two entries. And this one you can compute from the other three using that map, using that recursion. So t, well, x, y, z is 2xy minus z xy. Okay? So I'm just reformulating the recursion with a map. That's all I'm doing. But, so now that we have this map, we can study the map. And so the very first thing to note, actually, this may already be part. No, okay, so it's almost, okay. So the study of each example, each of the 5 examples, consists of, so if anything, the next 2 lines are the point of my talk, and then I want to explain what the 2 things are. The model independent part and the model dependent part. Okay, and so what are those 2? The first one is T. The map T is common to all of them, and I hope this has become clear. All you need is the Fibonacci substitution, which leads to recursion of the SKs, which leads to recursion of the MKs, and then if you have determinant 1, it leads to the recursion of the half traces. And that will be the same for all the examples. So T is the same map for all the examples, along with its properties that I will talk about. So, but why else are some examples more difficult than others? It's not only making the determinant 1 or making 4x4 matrices, 2x2 matrices. The really important distinction between them is the curve of initial conditions. Okay, so while the recursion is the same, coming from the same map T, the initial conditions are not the same. So the curve of initial condition is this guy, spectral parameter mapping to some initial 3 vector. So, and usually we take x1, x0, and x negative 1. And so the astute reader will now say, well, they aren't defined, and I say, yes, I agree. So x1 is defined. It's just a half trace across the matrix M1, which is as it's defined. But x0 is actually not the trace across the matrix M0, which in principle is defined, and x negative 1 certainly is not defined. So what do I mean? So let's define x1, 2, 3 as we did above, and then compute x0 and x negative 1 by applying T inverse to x1, x2, x3. So if you apply T inverse twice, you compute the 2 previous values, and that's what you use for x0 and x1, x negative 1. And the advantage of doing that is that as a function of E, this will become simpler. I'll show you how they look in the examples, and then you'll agree that this is the right way to start. Okay? But the point is that this particular curve is model dependent, and it's very simple in some cases, and it's very, very non-simple in some of the other cases. But it is what it is, and you have to work with it. Okay, so I'm coming to the third part, which is T along with its properties. So I've introduced T, and now let me talk a little bit about its properties. So 3 is invariant surfaces and hyperbolicity. Okay, so what are the invariant surfaces? So there is an invariant, Flick-of-Vogt invariant, which is the following. Let's look at I of xyz, defined by x squared plus y squared plus z squared minus 2xyz minus 1. So the 1 is just there for normalization reasons. So this is a function of the 3 guys, and the point is that I composed with T is I. Okay? So if you map T, if you map a vector by T, you don't change its invariant. So what this also means is that the level surfaces of I are invariant surfaces for T, and so this sequence of xk's, or rather 3 vectors depending on E, the invariant of the sequence of 3 vectors stays the same by this property. Okay, so let me write down the first thing I said here. So Si are the xyz's. So actually, so implicitly, I haven't actually said much about it, but I mean, so everything here is real, but you may also think about the complexification of everything, which sometimes is very useful. But for our presentation here, let's just look at real things. Okay, so here's a level surface. And because T preserves it, I can restrict it to it. So Ti is just a restriction of T to Si. Okay, so now I have a surface map. Before it was a 3-dimensional map, now it's a 2-dimensional map, a map on the surface to itself. And that is important because then you see the hyperbolic structure. So lambda I is the set of xyz's in Si, so that if you look at Ti applied to xyz, okay, and now you look at the orbit, and in fact 2-sided orbit. Okay, so you look at the 2-sided orbit of a point on the surface under this map, the trace map, and you say, okay, I'm looking at those points where the 2-sided orbit is bounded. Okay. And so this is the first theorem I will actually state explicitly. Theorem 1. So this was proved by Serge Cantat in 2009. Lambda I is hyperbolic. So I mean, there are more statements, but that's really the main thing. Okay, so it's a T-invariant set. It's a compact T-invariant set, so that at each point in the set, the tangent space splits into a stable and into an unstable space that are invariant under the differential. And the stable spaces, the differential contracts exponentially in forward time, and in the unstable spaces, the inverse of the differential contracts in backward time, or in forward time. Yes. And so yes, so that's to really answer Alan's question. So this is where, if you try any other substitutions, this is where things sort of part ways. Okay, so for all other substitutions, you have trace maps, you have recursions, you can do whatever you want with recursions, but this is where hyperbolic dynamics enters the picture. In the Fibonacci case, there's no substitute for that for other substitutions.
Why did Cantat study this specific map?
That's a good question that I can't answer. So, yeah, so, do you know? Okay, so I'm sorry, so you can ask him, so. But he proved it. And But that's an important input that really discriminates the Fibonacci case from most other substitutions we may care about. And
Maybe there is a partial answer, because the Fibonacci trace map is one of the maps that's known to be reversible. So as soon as you are on the surface, it's kind of natural to assume that there is a hyperbolic structure because it's conjugate to its inverse. So it's a natural map to try. And of course, you could then look for some other ones with similar.
okay, so a specific consequence of that is the following. So you have these surfaces. So this is Si, and then you have lambda I. So this is lambda I. And so for each point in the surface, you can then initially define these local stable sets and unstable sets, and then look at pre-images under T or T inverse, and then define these stable and unstable manifolds. Sorry. So if you have a point, you do have a stable manifold at that point, and you have an unstable manifold at that point. Okay, so that's just what you get once you know that you have a hyperbolic set. So this is so this X is in lambda I. Okay, so that's sort of the additional thing to play with that you don't see if you just work with these recursions, because the stable manifolds, they lie in the surface, and you can now connect points in lambda I to points that are not in lambda I. And in fact, this is exactly where the spectrally relevant points sit, namely the ones that are on the curve of initial conditions. Okay, so the curve of initial conditions consists of these points, which are functions of E. For each E, you have an invariant, so you get a point that sits on the corresponding surface. And so here, there may be some point of this form. So let me make the E explicit. Okay, and so now if you let E vary, you get this curve. Okay, so, and they may not lie in lambda I at all. And so somehow you want to relate them to lambda I, and this is what you use, in fact, the stable manifolds for. And so this I will hopefully explain soon. So I will first actually talk about these curves, and then I will tell you, how to make the connection between lambda I and the curve of initial conditions. Okay. So this is part 4, the curve of initial conditions. Okay, so discrete Schrödinger operators. Okay, so it's not on the board anymore, probably, but yeah, so discrete Schrödinger operators were discrete Laplace plus multiplication by V omega. And so the curve of initial conditions here is the following. So in principle, your spectral parameter lies in R. And then you want to compute the corresponding initial traces, or rather xk's. And so here you will see why I actually went back 2 steps and do not look at x1, x2, x3, but rather at this vector, because it becomes simpler. Because xk is a polynomial of degree fk, so already x3 will be a polynomial of degree f3. Okay? But if you go backwards, then you get nicer polynomials. And once you do that, then you see, for this particular curve, it's a line. This is a line in R3, right? And if you actually studied x1, x2, x3, you wouldn't get a line. And that's the thing. So you have initially a line, and then you map it under T and see how it changes. And of course, immediately it's not a line anymore. But for each iteration, you could look at the curve. Okay, so we just decide to look at the level 0 where you get a line. Okay, so this was known for a long time. And so by abuse of notation, I of E, I'll just call the invariant at that vector. So we want to know on which surface we are. Well, yes and no. So, I mean, so we want to know where the spectrum is. So we want to know which
points in lambda I or something like that.
Yeah, so we want to know which points are in the spectrum, and because by self-adjointness we know we sit in R, but in fact we sit in some compact interval determined by lambda. So we will always be in the interval -2 up to 2 plus lambda. So this is actually, so you could replace this by -2 up to 2 plus lambda. So there's no spectrum outside of this interval, and all the relevant questions happen in this interval. So you could actually look at a line segment rather than a line. The line is not the point. Okay. Okay, so, so the two things that you're interested in are the curve of initial conditions and which are the participating surfaces. For that you have to compute the invariant. And so here is why, another reason why the discrete Schrödinger operator case is simple, because it's one surface. It's an E-independent invariant, so everything takes place in one single surface determined by lambda. Okay, so this line actually is a line in the surface. Okay, so initially you have a line like this, in this particular case. Okay? All right, so for Jacobi matrices, so x1, x0, x -1. So again, as a function of a real E, and you could in principle restrict to a compact interval, or you let it run through the entire real line, here's what you get. So again, you get a line. I will tell you what mu is. Where A omega n is in 1 and mu, and B omega n is in 0 and lambda. Okay, so remember you have these two sequences, diagonal and off diagonal. Each one you get by replacing the A's and B's by either positive numbers or real numbers. And so for the A's, you just normalize things so that one of them is 1 and the other one is whatever. And for the diagonal terms, you normalize one of them to be 0 and the other one whatever. Okay? And so after this normalization, your two parameters are mu and lambda, and with those, you can compute the initial xk's like that. Again, it's a line. However, I of E, which is the invariant of this vector, is this here. It's E 1 minus mu squared, and so here you see it is in general mu, sorry, it's in general not E independent. Okay, so if mu is not 1, the invariant changes as you run through the E's. So this curve actually doesn't sit in the surface. So now you have this foliation, if you want, or lamination, that sits like this, indexed by I, and the curve cuts through them. Okay, so that's the picture that you get. But still, the overall setup is the same. You have this map, you have the invariant surfaces, and you have the hyperbolic sets sitting in each of them. And now you are looking at this static structure relative to these curves that you are determining here. And the invariant tells you which surfaces participate for any given energy. Okay, so this is the first complication in the Jacobi case, that now you're not working in one single surface. And so CMV, oops. So you have these two values. Those are the two values. Okay, so those are the two values, alpha, omega, n. Okay, so you replace A's and B's by two numbers in the unit disk, and then this determines your parameters. And then with rho, which is root of 1 minus alpha squared, and sigma, which is root of 1 minus beta squared, and k is 2, 1 minus real part of alpha conjugate beta. Okay, it doesn't matter. I mean, those are parameters now.
Alpha's on the unit disk. Oh,
No, on the unit disk, in the open unit disk. Yep. So x, 1, x naught, x negative 1, the curve of initial conditions. And now E is on the unit circle, right? Remember I said that the CMV matrices are unitary operators. The relevant spectral parameters are on the unit circle. So E is on the unit circle. And so here you get the following. You get E to the 1/2, E to the negative 1/2. And so now this, because E is on the unit circle, actually lies in this real interval. Okay, so that's an easy exercise that you get that, times 1 over 2 sigma, 1 over 2 sigma, 0, plus 0, 0, k over 2 rho sigma. Okay, so again, your curve of initial conditions is a line segment, and the invariant is the following. It's real part of E times something, 1 over 2 rho squared plus 1 over, well, actually, let me just write it down. So I think the main message here is that one can compute things and then look at what one gets. Okay, so here's the invariant, same story. In general, it's E dependent and cuts through the surfaces. Okay, so similar complication as in that case. And finally, so just to show that if you keep going along this progression of examples, things become even more complicated. In the continuum Schrödinger operator case, so continuum Schrödinger operators. So you have these local potentials that you replace the A's and B's with, and you can choose anything you want. And once you've chosen them, that determines your xk's, and in particular your x1, 0, and negative 1. And so in general, you can't compute things explicitly anymore. But still, they exist and are nice functions of the energy. But so in the case where you can still compute something, you just take these locally constant guys. Okay? So that's the picture I put on the board before. So either you place a constant obstacle or you don't, and the height is lambda for the obstacle. So here you can compute things, and so x, well, so actually, so you can compute x1, x, but I want to save time and not write it down, but I do want to tell you what the invariant looks like. Sorry, not a line segment, so that's what one observes here. So this is sort of the additional complication. So E dependent, but not a line segment, and I of E in this particular case is 1/4, and you get a 4, sorry, E lambda minus E sine squared root E sine hyperbolic sine squared root E minus lambda. Okay, so the additional complication here is the following. So not only are you E dependent, you meet the 0 value over and over again. Okay, so there are lots of E's for which this is 0. And I should have stressed that this is true for every I greater than 0. So at I equal to 0, things degenerate. And so the 0 case is a little strange. So, well, this is a Cantor set for every I greater than 0, but it's certainly not a Cantor set. It's actually homeomorphic to a ball for I equal to 0. And so the 0 case is special. And so the additional complication here is that even for positive lambdas, you encounter this 0 invariant case at many energies. This actually is an explanation for things that were discovered numerically. So in some physics papers, people talked about these pseudobands where the spectrum locally thickened up. And the explanation is that locally you have zero invariant where you want to be an interval. But it only happens at a point, so therefore locally there, the dimension, local dimension will be 1. And then you have positive invariant again, and your dimension decreases again. Okay, so I don't have much time left, so let me try to state 2 more theorems that then tell you what the analysis comes down to. So theorem 2, that's something I hinted at before. A spectral parameter E, which in most cases is in R, but in some cases is in the, on the unit circle, belongs to the spectrum of the corresponding operator. If and only if x1, so the corresponding point on the curve, lies in the stable manifold of some point. So x maybe is not, no, it doesn't matter. For some point in lambda I of E. Okay? So this sits in the surface with invariant I of E. And so this theorem makes the connection between the hyperbolic set, its stable manifold, and the curve of initial conditions. Okay, so this is how you transport information from your dynamically defined object to this curve, which in an often explicit way corresponds to a parameter space, which usually is a real line, where the spectral information can be read of. Okay, and so theorem 3 is the stable manifolds intersect the curve of initial conditions transversally. And so this comes in handy if you really want to transport quantitative information. So for example, many dynamical quantities on the hyperbolic set are what they are, and there are tools to study them. And if you have these smooth curves that you can transport information along that then intersect the relevant curve of initial conditions transversally, that just basically preserves dimensions and whatever you are interested in. And this then allows you to turn dynamical information from here to spectral information basically on here or E by pullback. Okay, and so because I'm out of time, let me just say that here I cheated a little bit. So this really is true for all the examples. This theorem was proved with Anton Gorodetsky and William Jessen only for the discrete Schrödinger case. And actually my plan for the talk, if I had time, but I don't, was to explain that for the other examples, one should be able to prove the same result. It's just we haven't done it yet. I mean, it's a long paper that proves that for the discrete Schrödinger case. But if you look at the proof and what it uses, it really tells you very clearly what you should be doing in the other cases. Okay, so I strongly expect that the theorem will remain true in the other examples as well. And so maybe there are some graduate students or Yuki maybe who want to work out some additional examples. Did you prove this for all parameter values? In some cases. Yeah, in the perturbative cases, right? No, yeah, so this, the point of this theorem is that it's a global theorem in the entire parameter space, whereas there were earlier results for large or small parameters. But then the final result was from 2016 where it's in the entire parameter space. So the main point is not to sort of redo a proof along the same lines, but rather, as I said, each of these operator families, they are of relevance to certain communities which are often disjoint. So you can actually prove results for certain classes of operators, which may be very interesting in the context in which they are studied and not really clear to the people working there. So in that sense, actually, it's well motivated to work out, similar things in a variety of settings. So with this, I close, and thank you very much.
Any question? Okay, then please stand for lunch, and I think that the lunch ladies will be very mad at us right now.
Again, yeah.